Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 3, Numbers in the Real World. In the previous sections, if you missed it, we went over percentages, the uses and the abuse of percentages. If for any reason you didn't have a chance to look at it, I strongly advise you to go back and take a look because in this video, we would focus or take a look on section 3B, putting numbers in perspective. So something you will hear probably a lot. Oh, sorry about that. So yeah, so we hear numbers in the millions, billions, or trillions, especially the US death or the US budget, all right? The world population is in billions. So, but the US debt or the US budget is in trillions, right? You see the US population is in millions because 332 something millions of people living legally in the US. So we heard about these numbers almost every day in contexts such as government spending, memory, storage also on your phone or your computer. Relatively few people understand what these large numbers really mean. So that's what we're going to study here. Several techniques for putting large or small numbers into a specific perspectives that gives them real meaning for us. So that's what we're gonna do. You know, working with large number or small numbers is much easier when we write them in this special format that we call scientific notation, right? So scientific notation is a format in which a number is expressed as a number between 1 and 10, right? So usually you take a number, you multiply it by 10 power something. So that M here, that number here must be between 1 and 10. So you see, we said can start with one, at least one, but no two digits. You cannot be 10. It's 9.999, but not 10. All right. So we can take any number. So we express number in this format by writing a number between 1 and 10 multiplied by a power of 10. Okay. So very important to see that. So a billion is 10 to 90 power. So if we said 1 billion, it's the same thing saying 10 power 9. Or you can say 1 and you do 9 zeros. Okay. So you understand that's 1 billion. So 10 power 9 is 9 billion. So we write 6 billions. If you want to write 6 billions, for example, 6 billion, that means is 6 times. Please put the multiplication sign like the cross. It's like 6 cross, not x, cross 10 power 9. Or if you want to see is 6, you can write it different ways, right? The same thing, but we're gonna focus on the scientific notations. Most of all, if we want to write 420 in scientific notation, let's say, for example, if you want to write 425. So if we can write it, because we can use only one digit, so we do 4.25 because you move the decimal point 2 units to the left, that means it's power 2, like this, right? So that means if you take 4.25 times 10 power 2, that gives you 425. So that's how we're gonna play and deal with scientific notations. Now let's see these particular examples. Probably you see it. If you that would be 6.7 times you count 3, 6, 9, that'd be 10 power 9. But here you have a 2, right? We're gonna say 2 times 10 power. Now you can count all these the numbers you see, the zeros C, including 2 to see the number. So we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that means 10 power 15. But because it's in decimal, we're gonna put a negative. Okay. Let's go with our first examples. Sorry for that. All right, we're gonna go with our first example. So we can rewrite a lot of numbers. Sometimes we can abuse them. We can say we write 10 to the power 2 pages of pages of books. So 10 power 2 is basically only 100 pages of books we read. So different ways of expressing, all those percentages. Rewrite the following statement using a number in scientific notation. Look, my hard drive has a capacity of 1.2 terabyte. So terabyte, recall that tera means trillions, right? So if you have 1.3 terabyte, that means is 1.2 times 10 power. Trillions means 12, right? Trillions mean 12 zeros, right? So that's power 2, okay? Because billions, 10 power 9. Trillions, 10 power 12. Million, 10 power 6. Thousand, 10 power 3. Hundreds, 10 power 2, right? So things you should know. For B, we said that the number of different 8-character passwords that can be made with 26 letters and 10 numerals is approximately 2.8 trillion. So 2.8 trillions again, as we said, we need to express 2.8 trillion. So that would be 2.8 times 12. But remember, the first digit that we call M cannot be two digits, all right? Cannot be two numbers. C, the diamond, we talked about the diameter. The diameter you know, um, of a typical atom is point 5 nano or nano. Nano means what again? Yeah, we call nano means billion. So that should be point 0.5. Or if you want, you can even include it, make it 5 if you want to. That should be 5. So point 0.5, okay. If we go point 0.5, that would be times 10 power 9, okay? Power 9. But because, sorry, negative 9 because is billionth is in the negative way. We need to go with that one. All right. So that's very important to see it that way. Now we see that's negative because nano, but because we need to have a number from 1 to 9, we cannot have anything below 1. So we're gonna change it. Is that for us we have 5 power 10 power negative 1 times 10 power negative 9, make it 5 times 10 power negative 10. So it's better you have your first number to be from 1 to 9. 1 point something, 2 point something, or exactly 2 or exactly 1, 9 point something, but no 10 or no 0 point something. All right. So we start using it that way. Again, they can ask you to do any types of excess examples here. For example, two, what they ask you to do is to multiply, they said estimate the following quantities without using a calculator, then find a more precise results using a calculator if you want. But you know what? If you multiply this one, because what I see if you want, that's 2.5. I mean, so we have for this one, we have 2.6 times 10 power what? 1, 2, 3, 4, and 5. So we can have 10 to power 5 times 2 times 10 power what to make it 200. Yes, thank you. 2. Now, if you want, you can multiply. The first thing, you multiply the products, right? So you can do 2 times 2 point, that make it 5.2. 5.2 times 10 power what? You see, if you have 10 power 5 times 10 power 2, we said when you have a power m times a power n, you need to keep the base and add the exponent. So that's exactly what we're planning on doing here. 5.2 times 10, 5. Oh no, I need space. I'm not gonna do it here. Let's do it down here. We have 5.2 times 10 power 5 plus 2. That make it 5.2. That make it 10 power 7. Okay. If we want, we can express it like this, 5.2, times 10 power 7. So very important, we can write it this way. The second one, we see we have 5, instead of say million like this one, remember 5.1 times 10. What is million again? Power 6, thank you. Times 1.9 times 10 power, how do you express 1,000? Power 3. Now, with a calculator, or if you want to, you can always verify. Now, you know you have, you know, 5.1 times 1.9. Okay, you can multiply these two if you want. All right, you can multiply these two. So that would give you 9.69 times 6 plus 3 because we need to add them. So 9.69 times 10 power 9. So that's billions. You either say it's 9 point, because for this one here, you can say it's 9.69 billions. The same way, the first one, you can call it a different ways. Very important, when you do the product. Now, if you look at the next one, okay, if you look at the next one, they say 600,000. So 600,000, that means you can take 6 times 10 power. Count the number of zeros you see. Yes, that's 5. Divided by 3.1 times what? 10 power 2. 3, sorry, because that's 3 digits. Okay, that's 3 digits because it's a 1, it says 2 zeros, so that's 3 digits. Now remember, we're doing divisions, all right? So what we have here is that you have 6 times 10 power 5 over 3.1 times 10 power 3. We know if you have a power m over a power n, you can subtract the exponent. So meaning we're gonna have 6 over, sorry, we can do 6 divided by 3. You know that if I grab a calculator, because even though they said, oh, do not use your calculator, I said, okay, I'm not gonna use it. All right. What's give me 1 second. I'm looking for I'm gonna do it with my phone. That would make it much easier. Oops. Okay, calculator. We have 6 divided by 3.1. That make it 18.6. No. 6 divided 6 divided by 3.1, 1 point, you know, 6 divided by, that would be 1.935. 1.935 times 10 power. Remember, you do 5 minus 3. 1.935 times 10 power 2. Because 5 minus 3 is 2. Okay? So if we want, we can still multiply because make it much easier to see we have a very small number, 193.5, because we can multiply by 10. So different ways of doing it. I'm hoping you can use what we do in part A to complete examples in part B. All right, leave it for you. But let's give some meanings to our numbers because, approximations with scientific notation, that's what we do. So giving meanings to our numbers, we are now ready to move towards our goals of putting numbers in perspective. As with problem solving, we did in maybe in chapter 2, I think we did a lot of problem solving. There was no single recipe for getting perspective, but a few sample techniques can be very helpful. We're gonna see a few of them. Perspectives through estimates. An order of magnitude estimates specifies a broad range of values, usually with one or two powers of 10, such as in the 10,000s or in the millions. So that's very important to see. It's like, well, if you ask a question, how high is 1,000 feet? Let's say a regular human being is 5.7 or 5.5, 5.7 feet. Now, how high is 1,000 feet? Maybe you need to look at some buildings. For most people, the quantity 1,000 feet has little meaning by itself. However, we can give the number some perspective by estimating what it would mean for a tall building, right? For example, we can expect each story in a tall building to be about 10 feet. Let's say 12 feet. Those are from ceiling from floor to ceiling, which means 10,000 feet. But if we say 10,000 feet is approximately a building with 100 floors, right? Oh my God, that's quite a lot. So keep in mind that estimates are not meant to be exact. I just give you something because some floors are that the height, is 12 feet high, all right? But it's just to give you an idea. Some estimates are useful even if they only get us within a very broad range of exact value, right? If you have an idea, then you can do it. So you can infer a lot about the character of the building by knowing whether its population is in the 10,000 or a millions. You know, that's very important. If you see some basketball players lately, they are very tall. Now, a building with only 10 feet height, maybe might be too low for them. That's very important. So estimate that give only a broad range of values such as in millions, you call that order of magnitude. So that's exactly what we do here. We're gonna just review a few examples and like this one where they ask you to estimate, in these examples, they ask you to estimate, to make an estimate comparison, discuss your conclusions. In the first one, what they ask you to do, maybe answers would vary, but let's do it. For A, which is greater, the amount you spent in a month on coffee or the amount you spent in in a month on gasoline. So this one may vary. It all depends. Let's say, for example, myself, if I buy a hot latte whole milk with no sugar, and a large hot latte costs approximately $5, not on the highway. So if I buy a latte per day, so in 7 days, that make it $35 per week. But do I need $35 for gas every week to go to work, or would I need more? Well, again, here it will depends on the type of vehicles I drive. It will depends where I buy the latte. So that's why I said this answer would be valid regarding the estimate made. But most of you know, let's see. Yeah, okay. So I would say most people spend more money on gas each month than coffee, right? If you buy on average one coffee per day, you're spending $3 per coffee. That's around $90 per month. On the other hand, if you fill up your gas tank once a week, spending about $35 to fill that tank, right? So assuming a 12-gallon gas tank, I mean $3 per gallon. So that's approximately $150 you spent per month in gas, right? So it all depends. Some people don't drink coffee. Some people would drink latte. That's about $5. Some people will drink only regular coffee. That's $2 and $3. Even one coffee per day for $3, that make it $90, but gas would be 150, right? So if they ask you another questions, could a person, I mean, we said the first questions may vary. It all depends of, perspective. Could a person ride a bike across the United States in a month? If not, about how long would it take, right? New York to California. Again, here, answer was vary regarding the estimate made, but it's certainly possible to ride across the United States in a month. If you would at a modest rate of 12 miles per hour for 8 hours every day, you would be riding 90 miles per day. Over the course of 1 month, 30 days, you would end up riding 2,880 miles, which is almost enough to complete the trip because the trip is about 3,000 miles from New York to California. So if you want to ride your bike from New York to California, that is approximately 3,000 miles. We said if you do 12 miles per day, we're talking about B, right? For B, 12 miles per hour, riding your bike, 12 miles per hour, 12 hours per day, right? That make it 8 times to 6, so that's maybe 96 miles per day for 30 days. So that's why we said if you multiply all of this for 30 days, that gives you approximately, 9 times 0, right? 3 times 6, 18, 3 times 9, and that make it 28, right? So that would be 28 miles in 30 days in for 1 month if you do it. So that means you're gonna be pretty close. About 1 month, yes, you can cross from New York to California with no problem. As we said, that would vary. Could an average person lift the weight of $200 in quarters? Again, here those are things so that you can say, oh, okay, let me verify if it's possible or not possible. So you assume a quarter weight. How many quarter? I mean, weight of a quarter, right? Weight. How many? I think it's 0.2 ounces, right? So you see, you need to know the measurements, but you can do also the math. So the weight of $200 in quarters would be approximately, if you take how many quarters is $1? $1 for a quarter, right? Right? So that means $200. We're talking about C. So $200 times 4 is 800 quarter, right? So if you have 800 quarter, and you multiply it by zero point 0.2 ounces, approximately that's only 10 pounds. Yeah, it's like the weight of a luggage, sweet carry-on. Sorry, so carry-on. So you assume that, of course, it's possible. Yes, assuming that like this, it is possible. Now you get it. I usually leave one for you. The last one is for you. Now, make order of magnitude of estimates. Remember, we said magnitude of estimates is when you talk like in millions, in thousands, when you make estimates, right? Um, Now, let's see for the next examples what we can do. They said make order of estimate of the following quantities. Okay. Again, those are everything you can explain. That's what we're gonna do. Maybe do one or two of each. Total annual spent on a pizza in the US, right? You want to make an estimate of that? Total annual spent on pizza in the US. This said, it's all depends. Really, it's all depends because I believe they said 100 million pizza eaters. That would be every day. So, I think we have 100 millions of people eating pizza in the US. One pizza per day for 1 month. How much approximately is a pizza? If you eat, if 100 million pizza are eating every month, one pizza costs, I mean every day, sorry, millions. One pizza costs approximately how much? Let's say in some places one pizza costs $15. So, you know, it's only 100,000 people eating pizza per day, 100 million. So, what we mean by that, if you take 15 times 100 millions, that make it, oh, that should be more. Hold on. 15 times 100, 1, 2, 3, 1, 2, 3, one more zero. Yeah, that should give you $1,500,000,000 pizza per per day, right? So that's what we're gonna eat. That's what we eat every day, right? 1 billion. That would be only 1 billion. Now, if we do it, that's for 1 month. Sorry, one pizza per person per month for that's for per month because not per day because they said approximately everyone eat one pizza per month, right? Here, if you do it for 12 months, that gives you 18 billions of dollars. So 18 billions of dollars, we're gonna say that's the price we eat for pizza in 1 year, all right, in the US. So that's kind of an examples for A. As we said, we make order of magnitude. We do estimations. What we said can be the exact, but it gives you also an idea. You know, if we said the total annual spending on movie tickets in the US, right? Again, here, that should be kind of estimate of what what we're gonna say, right? Um, let's say how many people goes to the move to the theater, watch movies every day. So total annual spending on movie tickets. So approximately, if you go over the internet, you check. That's I do my own research on this. So about 200 million people goes to the movie theater to watch the movies. So per month, okay, 200 millions per month. Let's say suppose the tickets for one, what tickets is $10. So if you have 200 people going per month, you just need to add another zero, right? You have 200 million, so that gives you 2 billions, right? Because we added by $10. If you multiply by 12 months, also again here, it would give you approximately 24 billions, right? 24 billions of dollars make on you know movies every year. So one ticket per, I mean, 200 people goes every month, approximately $10 per ticket for 12 months. I mean, keep 24 million. So those are examples of, you can do. But at some point, also, we have some tables that we can follow because those tables are very important when we talk about comparisons, when, perspective through comparison. So that's the second way to put numbers in perspective. We make comparisons. Like if you, for example, if you consider $100 billion, a number that you may find in the news almost any day, it's easy to say $100 billion. But how big it is, 100 billion. So let's take the net worth of the current richest person in the world, which is about 100 billions of dollars. How big is that number? Let's take of it in terms of counting. Suppose you were asked to count 100 billions in $1 bills. How long do you think it would take you to do that? If we assume you can count one bill each second, so I mean you need to go from one. If you can, suppose you can do it from one digit per second, which is not true because after some millions, you cannot do it in second. Even though you could do it in second, it would take you, like 100 billion seconds, to do that. But that's still not very meaningful. However, we know that there are 60 seconds in 1 minute, 60 minutes in 1 hour, 24 hours in 1 day, 365 days in 1 year. So if you want to count $100 billion, okay, using only dollar bill, $1 bill, it would take you approximately 3,171 days to count that amount of money. So, in other words, 100 billion seconds and 3,171 years represent the same amount of time. By saying 3,171 years makes the amount of much easier to understand because if we said 100 billion seconds, it doesn't make any sense also. But if you take 100 billions, you divide it by 3,060 second. Okay. So let's do it. I'm gonna try to do it in this calculator if I can, of course, because not all calculator would let me do it. 100 billions, one, two, three, one, two, three, one, two, three. We divide that by 36 hundred. 3,600 for us means 1 hour is 36 seconds. 1 hour is 3,600 seconds over 3,000 because 1 minute is 30 seconds is 60 seconds. 1 hour is 60 minutes, right? Okay. So we understand that this number right there can be 277. Let's say they just change it by it give us. I mean, I'm gonna do it different ways just to show you what we mean by that. We're gonna have 27 times 10 power 6. Okay. Oh, that's in millions. Now we said that now we know it's an hour per hour. That's hour. So if we take the same number and divide it by 24 hours for 1 day. Okay. So if we divide it by 24 for 1 day, it gives you a simpler number. So now we go down to 1,157,407.4. Now we need to divide it by 365 days to make it annually. Divide by 365. Yep. So approximately, as we said, that's how it's gonna give 3,170 71. Let's say 71 because there is a big decimal. So it takes you 300 3,171 years to count from 1 to 100 billions. No, like you were going to take only 1 second per for each, which is not true. You're gonna take longer than that. All right. For the record, human beings cannot live more than 120 so far. So no, you cannot do it. So you understand what it means. So perspective through comparisons is very important that we tells you this and show you at some point that table, this table we give you here to that's very helpful. Okay, so it's select that's help you to select energy comparisons. All right, that will probably be useful. But let's go with the last examples. In these examples, we ask you use the table that I just showed you here to answer the following questions. So we can answer as many questions as possible using the table. So we can use the table to do that. All right. Let's try if we go with we're gonna go with C. All right. Compare the energy released by burning 1 kilogram of coal to that released by fission of 1 kilogram of uranium 235. So you see in this one, what they ask you to do, 1 kilogram of, because let's say C, I'm writing C, 1 kilogram of uranium 235, release, we can go back down here. 1 kilogram of uranium, so we are right there. Okay, for the C, we are right there. We said it's released 5 okay, 6 times 10 power 13. So you can look and verify what I said, joules, okay? That's in joules, okay? Um, which is about 1 kilogram. That's about 35,000, which is 35,000 times as much, okay, 35,000 as much as the energy, as much as energy released, by 1 kilogram. I'm gonna put kilogram kg, all right, of coal. Okay. What is the 1 kilogram of coals? Let's go back to see. 1 kilogram of coals is 1.6 times 10 power 9. Okay. So you can see that of coal, um, which is 1.6 times 10 power 9 joules. Remember, we have those in the parentheses. So for us, so you can see that 5.6 times 10 power 13 over 1.6 times 10 power 9. That gives you 35,000. Right? So that's how we find it. So I do one of these, it's just to show you, but we could do A if you want, because for A, what they ask you, how many average candy bars would you have to eat to supply the energy needed for 8 hours of running? So in the table you need to see, the text said that 4 million joules are required for 1 hour of running, right? Because 4 million joules energy for 1 hour is right there in this second. 4 times 10 power 6, that make it 4. 4 million joules are required for 1 hour of running. And that average, candy bars surprise 1 million joules of energy, right? One hour candy bars, you can see it here, provide about 1 million. So 1 times 10 power 6, that's 1 million. Now they want you to know, to state, how long is it. So 4 candy bars would be needed for each hour of running. So which means that you would need about 32 candy bars to supply it, So that would be 32 candy bars. Yes, please, you need to make the comparison using the previous tables. I hope that's helped to do all the other examples. I'll come back in a different video to talk about dealing with uncertainty. In the meantime, if you have any questions, do not hesitate to reach out. Take care.